C. Lindelof AP Calculus maximum volume problem from optimization, and we're asked to determine the dimensions of a rectangular solid with the square base with maximum volume if its surface area is 337.5 square centimeters. Sorry about that. So remember, when we're looking to do an optimization problem, we need two equations. We need a primary equation and a secondary equation. The primary equation is the thing that we're going to maximize, and we're going to maximize volume. So the first thing I'm going to do, if you don't mind, is I'm going to actually draw a little picture. I'm going to draw a picture of this thing. So here's my rectangular solid, like this, and this. So there's my rectangular solid. It has a square base. If you don't mind, I'm going to let the base be x by x. And then we have this height. It's rectangular. It does not say that it's a square. So I'm going to make it h. So what I'm going to do first is I'm going to say, well, the volume of a rectangular solid is, in our case, x squared h, isn't it? X squared h, because we do have the square bottom. And that's our primary equation because we're supposed to max that. So here's our primary, and your professor wants to read that. So primary equation is this one. So there's our primary equation. Then we need a secondary equation, and our secondary equation is going to be surface area. So I could say that the surface area of this thing is going to be, let me show you how I'm doing it here. I'm gathering this up. I'm like, okay, I got this surface area here, right down here, and then there's a like one here. Just like one right here. So I'm going to say that there are two of them, 1, 2. So I have 2. The area of a square is x squared plus the sides. And we have 4 sides. Let me show them to you here. Obviously, there's a side here. There's a side in the back here. There's a side here. And there's the side across the front. So we have that. So we have 4 of those. So 4 of those sides, and each of those sides has a base of x and a height of h, so 4xh is our secondary equation. A lot of professors prefer this to be called a constraint equation either way, and the reason that this is a constraint is because they give us this here. They say that the surface area has to total 337.5 square centimeters, so it's 337.5. So this actually looks pretty good. The problem that we're going to have here is that I want to take the derivative here because I want to get this rate of change of x, but we're stuck with this h. So we have 2 variables here, and that's not okay. So this is going to happen most of the time when you're doing a problem like this. So there's h here. So I'm going to go ahead and I'm going to solve the secondary. I'm going to solve the secondary equation in terms of h. So I got h is equal to 337.5 minus 2x squared all over 4x. So I think that works out good, doesn't it? So what am I going to do with that? From there, I'm going to plug this into, plug into the primary. So plug into primary. Plug this into the primary equation. The routine that we're using here can be used over and over and over again. So if you can do this problem, you can do any problem, is the good news. So I'm going to go ahead and sub that in. I'm going to say that I want the volume of a rectangle to be maximized. I start with this x squared. This x squared is obviously this one. But this h right here is this h, and it says clearly that h is this. So I'm supposed to multiply times h, and h is 337.5 minus 2x squared all over 4x. So here, I think it would be really smart here if you just slow down for a second, because what we're going to want to take here is we're going to want to take dv dx. We're going to want to evaluate the change in volume as x changes. But if you look at it in the way that it is right now, this is a crap storm right here. Right? It's product rule here, it's quotient rule here. It would be so much easier if we could make it sum and difference rule. So that's what I'm looking for. We have x squared here, and we have x to the first here. So x squared cancels, right? Cross cancels there. Then what I'm going to do is I'm going to distribute this x into here and here, And then I'm going to factor out this 1/4, and I hope you can see it. This is 1/4. So I'm going to factor out this 1/4. So as I do both of those things, it'll look like this, that the volume of my rectangle is actually 300, actually is, look, this one, I'm going to pull this 1/4 out first, times 337.5 times x is 337.5x. X times negative 2x squared is negative 2x cubed, right? So if you look at this second equation here and compare to this one, this will be a hell of a lot easier to differentiate. Now I'm going to go ahead and differentiate, so I'm going to take the derivative of volume with respect to the change in x. It's really important that this is this and this v is this one. Otherwise, you could, just to get away with one, you could just say I'm taking v prime, and you could get away with that for sure. So dv dx is equal to 1/4 times 337.5 minus 6x squared, isn't it? 6x squared here. So we're going to want to set this thing equal to 0, aren't we? So now we're going to look for our critical values or our critical numbers. So I'm going to call it critical value. And critical value is where a derivative goes to 0. So we want to set the whole thing equal to 0. So we want the whole thing equal to 0. So we want 1/4 times 337.5 minus 6x squared to equal 0. Multiply both sides by 4. Right? Multiply both sides by 4. This goes to 0 also. These parentheses go down, don't they? We get 6x squared is equal to 337.5. From here, we divide both sides by 6, and we get x squared is equal to 56.25. Looks like crap. This is calculator math, so the fact that I know this answer, don't be too impressed. When I take this derivative, when I take the square root of both sides, so this thing does come out pretty clean. It comes out to be 7.5. So the dimension, so we have the x dimension. Now we need the h dimension. So go back up to h, plug this in, plug in the 7.5 squared, 7.5 here. Believe it or not, when you do all this arithmetic, you get back that, now I'm not really surprised, you get back that h is equal to 7.5 centimeters also. So 7.5 centimeters. So the maximum value does occur when x is 7.5 and h is 7.5. What I did was, really quickly, is I took the second derivative and made sure that it fit, and it does. So these are my answers. X should equal 7.5 centimeters, and h should equal 7.5 centimeters. Okay, hope this helped you in some way. If you have any questions or comments, please let me know. If you haven't already subscribed, please do. Thank you.